the Sustainability Management Master's Program, you are answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. At the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
Okay, so I'm just going to dive right in and talk about sustainable remediation, kind of what the current practice is and where the industry is moving towards. So before I dive into sustainable remediation, I always think it's important to revisit where did the concept of sustainability even come from? And this came from the Brundtland Commission in 1987, where they were focusing on how can we utilize non-renewable resources in a manner that is available to meet similar or equitable quality of life standards for future generations, right? That seventh generation type of principle. But since then, it's really developed into this concept of the triple bottom line, where you're looking at these three individual spheres. You have your environmental sphere, your social sphere, and your economic sphere, with your sweet spot being in the middle to optimize sustainability. Now, what I really like about this Venn diagram is that these spheres overlap each other, right? So if you have a detrimental or positive impact in one of these spheres, it's going to influence the other two spheres within that triple bottom line. So it's very important not to think about sustainability triple bottom line in silos. They're actually spheres that interact with each other and often overlap in their metrics and the way that you're evaluating these different types of indicators. So make sure you get that multidisciplinary background so that you're able to truly look at it from a triple bottom line perspective. So sustainable remediation is the concept of protecting human health and the environment from hazardous waste or contamination throughout the project lifecycle. And we want to ensure that we minimize our environmental footprint, but we maximize the benefits to the social and the economic sphere at the same time. So for a quick history of sustainable remediation, I mentioned SURF earlier before, the Sustainable Remediation Forum. This organization developed the first white paper on sustainable remediation, and that's concept of how we need to look at the triple bottom line when we're looking at different treatment technologies and how we're selecting the technology that we're going to implement on a project. That was followed by the Environmental Protection Agency guidance in 2010 on green remediation. They solely focused their guidance on the environmental sphere as opposed to the economic and social sphere. And their perspective behind that is that they consider the economic and social spheres as part of the National Contingency Plan, the NCP criteria, that is a set of 9 indicators and standards that you use to help you identify which technology you're going to implement. And as part of that, community acceptance is an indicator, and also financial feasibility. So they said they were incorporating those already as part of that process. 2011, ITRC, which is the Interstate Technology Regulatory Council, developed a green and sustainable remediation guidance. You might hear that term a lot, GSR. ITRC is really great if you are in the remediation field because they work on technical initiatives that are in cutting edge science for remediation. You can join these technical initiatives through academia to help work on guidance documents. And oftentimes state or regulatory agencies will just adopt the ITRC guidance without even making their own. So that's a really cool organization to look into. ASTM came out with standards after that. And then the National Research Council, NRC, came out with a new concept that said, you know, as we're considering sustainability, let's make sure we're marrying this with risk management and having this discussion of sustainable risk management as early as possible in the project life cycle. And I'll go into that a little bit more in the future slides. And then that just led to federal agency and states and other corporate parties developing their own guidances internally that are used. It's also an international initiative. Cert has chapters all over the world, as you can see. And most recently, ISO, which is the European standardization protocol that they came out with a sustainable soil remediation guidance recently that they're using in Europe. The next international Cert conference is in Brazil in November. If anyone's interested in that, I'm on the planning committee and be happy to talk to you about that. Okay, so sustainability assessment process, and this is pretty much the current status of how we're going about performing sustainability assessments for remediation projects. The first step being preparing your data inventory. And what I mean by that is getting a really good understanding of the different components that are making up the remedial technology that you're considering. So if you're considering pump and treat, those components will include the wells you need to put in the ground to extract the water, bring it to the surface, what type of media you're treating that water in, such as carbon, and then how you're dealing with that wastewater. For something that's in situ, like bioremediation or chemical oxidation, again, how are you injecting that material in the ground, the footprint of those materials themselves, and any waste products. So all those different components that add up to that particular remedy, and then you create that data inventory. Now, what's really great about the remediation industry is that there's a lot of environmental footprint tools out there that make it easy for you to calculate the environmental footprint of different technologies. These were developed by the Navy, Battelle, and Army Corps, came up with SiteWise, which is on its third version, and you can do any type of treatment technology from groundwater, soil, and sediment within that particular tool. The CEFA tool, which is the Spreadsheets for Environmental Footprint Analysis, was actually developed by EPA. Now this tool has, go ahead.
Both of them are public domain, right?
Both of them are public domain, correct, yes. So they are publicly available. And they're Excel spreadsheets that you use with drop-down menus and stuff. Now, because they're generic and they have drop-down menus, sometimes you're utilizing a component of your remedy that's not in that tool, right? You might be using a type of amendment that a vendor is providing, like AquaBlock or something for your sediment. So then you'll need to calculate that footprint using life cycle assessment and input those carbon dioxide equivalent factors into the tool itself. So that's another step. You always want to do a community impact evaluation, which is very qualitative. How is the remedy impacting the community? And some examples would be if you're doing excavation, is there a lot of truck hauling traffic that's going in and out of the community? Is that disrupting the business and quality of life for the community that's nearby? What is the redevelopment time frame for your remediation? How can we bring this back to a valuable asset for the community? So kind of incorporating that as part of your analysis. Also, we're bringing in social costs. So this helps you link environmental footprint metrics such as carbon dioxide emissions, NOx, SOx emissions, energy use, and giving a link on how those metrics contribute to climate change impacts and how those metrics contribute to regional human health impacts. And that's what these social costs of carbon or the social costs of these other chemical emissions represent. And then you can put that into a monetary value to help with your analysis. Once you go through that process, you want to identify what your sustainable technology is. Implement best management practices to help optimize the sustainable attributes of your remedy. ASTM has a great list of sustainability remediation BMPs. And it's important to constantly revisit the remedy and optimize it. As part of remediation, a lot of the time that technology is going to be in the ground over an extended period of time. And if it's being regulated under EPA, you have a 5-year review where you need to revisit what you're doing after a 5-year period and decide, is this still working the way I want it to work? Do I need to transition it to a different technology? So always consider sustainability in every phase. Also, resiliency. So how are the remedies that we're putting in place are resilient to climate change impacts that may affect the remedy? And EPA developed these climate change adaptation technical fact sheets. And there's 3 of them. There's one for contaminated sediments, landfills and containment, which you can also use for stabilizing, like capping soils in the ground, you can use that. And then groundwater remediation systems, which include pump and treat, but also in situ treatment with injections and other type of in situ technologies. And that's, you could just Google it, you'll get it. All right, so I'm going to go through a case study, kind of dive in and give you an example of how this is done. So this case study is from a Navy site that I have the pleasure to collaborate with the Navy on. And the main contaminants for this site is metals and PCBs, which are in the sediment due to historic operations that occurred on site, after periods of time, either that contamination infiltrated through the subsurface, got into the groundwater, and seeped into the sediment, thus settling out, or there was operations going on along the piers above water that also led to the contamination getting into the water. The exposure pathways is the benthic community, so you have like clams and worms in your sediment. They get eaten by little fish, they get eaten by big fish, and then eventually up the food chain to birds and us. So there's a pretty extensive exposure pathway there. And since this is a sediment site, the remedial technologies that were considered was removal, so dredging, in situ treatment, so treating that contamination in place by adding amendments, capping the sediment to prevent that exposure pathway from happening, right? So if you have think about an asphalt cap, you can't interact with the soil beneath it, same concept. And then monitor natural recovery is taking advantage of natural processes to degrade the contamination that's there, either through degradation that's happening naturally by bugs and other microbes, but also with sediment, it also takes into consideration deposition of clean sediment onto the contaminated sediment, and that's part of monitor natural recovery. Now, you might have heard monitor natural attenuation with groundwater, which is very focused on the degradation of contaminants by bugs and so forth within the groundwater. But for sediment, it's monitor natural recovery. It's two different concepts. Okay, so when we were trying to figure out what is our best technology to implement, we had three different main drivers. We had site-specific drivers, which are associated with like the geophysical and hydrological characteristics of the site. We did a sustainability assessment, and we also did a resiliency assessment. And what you're doing is you're utilizing each of those three types of evaluations to give you the best informed decision on how to move forward with your remedy selection. So for site-specific drivers, we looked at contaminant concentrations. And here, when I say not to exceed preliminary remediation goals, PRGs are goals that you work with the regulators and other stakeholders to determine, what is the end game from our treatment? Like after we implement this treatment, what is going to be the final concentration of these contaminants that are going to remain in the ground? And there's different types of standards and site-specific human and ecological risk assessments you can do to help you come up with those values. And those are called PRGs in EPA land. We also know that based on a pilot study that we did, that we get a 90% reduction in the bioavailability of PCBs using carbon-based amendments. So that's another aspect of our contaminant concentration. But it's also important to note that in situ treatment is not effective for metals. So if we have an area that's contaminated with PCBs and metals, in situ is not going to work, right? Because we're not going to be treating that co-contaminant. So it's very important to understand what all your contaminants are and the drivers behind how you can remediate that. For water depth, it was important for us to understand where the intertidal and the subtidal sediments were and how wind and wave action and turbulence affected these areas, especially during severe weather events like the 100-year storm. And also receptors. If we were deeper than 30 feet, we didn't have that complete exposure pathway anymore because the birds that were eating the fish and interacting with that benthic community were not within that habitat. Oh, excuse me. Yes, the surf scooter. Hydrodynamics, again, looking at currents, tidal currents, and impacts of wave action on your different technologies. Natural recovery, how much time is it going to achieve background concentrations? And that's a really important factor, especially when it comes to if you want to move forward with redevelopment. If something you're going to implement is going to take 100 years to clean up or attenuate, and you're not able to return that to a valuable asset to society, does it really make sense to go into that direction, right? What other type of controls can we put into place to ensure that we're moving forward with this redevelopment and bringing that site back to a valuable asset? And then constructability, especially when you're talking about working in the shoreline and sediment. A lot of time there's debris along the shoreline when you're working with like an industrial area. Is that going to impact the type of technology that you can implement? And managing dredge soils. So this is the results of the sustainability assessment that we did. I'll go over it. And over here you can see these are the, sorry, I got it. These are the treatment technologies that we looked at for a specific area, Area 3. So we looked at just complete removal, removing out all the contamination that was in the ground, doing focus removal and putting a cap, so either an armored cap or a aqua block cap, So there's just two different types of caps you can put in the ground. And then alternative 4 was removal, just a smaller removal area. And as you can see here, this is an environmental footprint analysis using SiteWise. The orange is the amount of energy that is used to implement the technology. The blue is the amount of greenhouse gas emissions that are implemented for each technology, and then the gray is how much water is consumed. And what's really great about SiteWise, it breaks it down to consumables, equipment use, and miscellaneous. So consumables would be amendments that you might be putting in the ground, PVC piping, and other type of raw materials that you're going to purchase for your remedial action. Equipment use is going to be drill rigs, the boats that you got to put out there to, help either place that amendment or do the dredging, and then residual handling is dealing with the waste. So overall, you can see, of course, as we refine our removal area and maximize where we're doing the capping, we were able to reduce our environmental footprint significantly under alternatives 4 and 4A. And then these are just a couple of other metrics that you also get from SiteWise. You get total SOx emissions, which is a pretty light color in this. I don't think you can really see it that well. The gray is total PM10, so that's coarse particulate matter. PM 2.5 would be fine particulate matter. And NOx emissions, NOx. And then it also does accident, risk, and injury as well. So how long is someone actually operating equipment, and what is the risk of that person being involved in that scenario on site? And again, alternatives 4 and 4A were pretty low. So this is relatively straightforward, but it's still a lot of metrics, right? We have to look at 2 different graphs. It's all over the place. How can we process this into one type of metric for ease of comparison? And that's where I like to bring in the social costs. So I bring in the social costs of greenhouse gas emissions, NOx, SOx, PM10, electricity, so I can bring all those metrics down into one monetary value to help me compare these different alternatives to each other. And then you can see how much of a difference alternatives 4A and 4 are from the other alternatives we were looking at. Now 4 and 4A, their differences were in the capping material that would be implemented. And I would say that this type of footprint analysis has a little bit high of a standard of error. It's very high level that we're doing this type of analysis for, so I wouldn't say this is a huge difference. I would advise that either of those capping options would be fine. If you wanted to look at it more deeply, do life cycle assessment, because that will really bring you down into the nitty-gritty of things. So what we did was we took that sustainability assessment and our technology framework and came up with a really nice flow chart to figure out, okay, what are the areas on site that we can implement these different technology footprints, right? We're doing a multi-component remedy. And that's mostly what we do on sites. We don't just go out and do one remedy. We don't just go out and excavate or just do in situ bio. The site itself is very complex, and oftentimes we're implementing more than one type of technology on a site. So for here, we don't want to exceed what our remediation goals are. For areas where it was too shallow for capping, so the wave action was interacting with the sediment too much, and if we put a cap down, it was going to be scored, and there's going to be a lot of turbulence. So we can't put a cap there, so we're just going to have to go in and excavate it out, right? And the water that what was deep enough for us to cap, but was less than 30 feet, right? Because above 30 feet, we didn't have that exposure scenario. Then we put down the cap. So kind of using that decision framework to help you assign the technology footprints. We'll just go through another one of those exercises here, where we looked at another area of the site. Alternative 2 was excavating out all the material, which is also always very expensive. Alternative 3 was just doing in situ treatment of the whole contaminated area. Alternative 4 barely has an environmental footprint, and that's because we said, what if we did nothing on site and we just let monitored natural recovery, degrade and have that sediment deposition and decrease that exposure scenario and concentration over time. Alternatives 5 through 6 down here, they were just different removal scenarios. Right? They're just different removal scenarios, yes, and different types of backfill. So sometimes when you remove contamination from the ground, you, instead of just putting clean backfill, you'll mix it with some amendments so that when you stick it back in the ground, it's interacting with whatever contamination still may be there. So you could mix it with like carbon and other types of materials. So we started off with just 2 through 6A, and we did our footprint analysis. We didn't do 7 yet. And 3 and 4 were coming in pretty low. 4, we were like, we want to be proactive. We're not going to wait like 100 years for this contamination to degrade, because then the client's liable, right? I mean, he has to take care of, that person has to take care of it, or that entity has to take care of it for that whole time. Alternative 3 was looking really promising, but the in situ treatment didn't work in certain areas where there was high tidal action. And from our technology framework, we didn't feel that it was going to be technologically feasible for us to do that type of remedy. So we developed alternative 7, which was a hybrid of removal, in situ treatment, and natural recovery. This is just showing the results again from those different metrics, but what I like to show is, again, how can we normalize all those metrics down to one value so it's really digestible for the client, for the public to just see just one graph and say, okay, we understand why you're going with the particular scenario. So we suggested going with alternative 7. And again, came up with a nice flow chart to help us communicate this. So if we do not exceed remedial goals, then there's really not much for us to do. For this particular site, within the San Francisco Bay, the San Francisco Water Board did a evaluation to determine what the concentration of background is at the site, right? Because it's a historic area, it's heavily been used. So within that bay, PCBs are typically at a concentration of 200 ppb. So a lot of the time, even if a standard is below background, you don't have to clean up below background. So you'll get that acceptance by the regulator and other stakeholders that you can just clean up to that background concentration, and that's what that 200 is. Again, metals and PCBs had to be treated differently, right? Because we can't do in situ treatment with metals, so we just went in and removed that and installed some backfill. For PCBs, we wanted to do in situ treatment, but again, we only could do it in the subtidal area, not the intertidal area where it's really active with the wave action. So if it was intertidal, we had to remove it. If it was subtidal in that deeper water depth, we then had to look at what is the feasibility of this amendment to reduce the concentrations down to that background concentration. So earlier, we said that there was a 90% reduction in bioavailability by implementing that amendment there. And doing some modeling with sediment concentrations and so forth, and with the pilot study, we determined that if there were concentrations above 12,400 ppb, that amendment was not going to get us down to background level. So we had to go and remove it. And then if it was between 12,400 and 1,240, we did some in situ treatment, and if it was below that, we just let it go, M&R. So again, taking that multi-remedy component approach. And what this does, it helps you refine your treatment footprint, but it also helps you be more sustainable. Because what do we see from the sustainability assessment? The excavation removal had a really high footprint, right? So we want to limit that as much as possible. But you're going to have to do it in some situations of the site. So how can we refine it to make sure we're limiting the amount that we're excavating? Similar with these other type of treatment technologies. For the resiliency evaluation, we looked at climate change impacts and how the different treatment technologies were vulnerable to those impacts. So one impact was, there's going to be an increase in surface water flow, currents, wave action due to more severe weather events. And this is going to potentially score a cap or the underlying amendments that we're putting into the ground. So there's best management practices associated with cap enhancement, where you're doing protective layers on top of the cap to help kind of mitigate that type of scoring. There's different types of amendment settling processes. So, you can get a hopper where you're just kind of like spreading out amendment, right? You're just like spraying this amendment in everywhere. Or you could be a little bit more diligent with doing more focused placement so it doesn't get dispersed within the water body. The severe weather events will also resuspend that sediment, and we want to make sure that we're designing our remedy to take that into consideration. So when we do hydrodynamic modeling, we're looking at the 100-year storm event. What is going to be the tidal currents and the hydrological processes that are going to be there during that severe weather event, and let's consider that as part of our remedy implementation. But also, what is that 100-year event going to look like in the future? So you can project out how precipitation is going to increase over time, how wind is going to increase over time, and project out what these storm events will look like in 100 years and model in that type of scenario. And a lot of resiliency work is going in that direction too, not just remediation. And then vulnerability monitoring. Let's monitor precipitation, wave action, wind speed while the remedy's in place, and see if we are seeing these increasing trends over time. So what we were able to do, we were able to implement a remedy that had an environmental footprint that was 42 to 75% less than what we originally thought. We were able to meet the NCP criteria, which is the criteria EPA requires us to meet when we implement a remedial action. When we go through this process, it helps us identify sustainable best management practices we can implement during the design, right? We didn't even get there yet. All we did was identify types of technologies that are possible, what type of technologies we're going to implement and where, and then as an environmental engineer, now you need to design it, put together specifications, put together these design documents to help us actually go in and the contractor to implement that cleanup. So you integrate best management practices as part of that process. So you want to look at low footprint consumables, so what kind of capping and amendments we can do that have lower footprints, limiting our residual handling, so we limit the amount of sediment that we're extracting, but let's try to find ways to reuse it. A lot of the time when we're extracting the sediment out of the ground, there might be an area that is deemed non-hazardous, and it can be used as backfill in other places. So let's explore those type of reuse scenarios that are available. You can also consider clean diesel retrofits. That's a big push by the EPA, and they have a whole document on that to integrate into your drill rigs and other type of machinery. And again, we went over the resiliency adaptation measures. I'm just going to touch upon another case study. only have a couple slides on this one, but just showing a different type of site. So this particular site, we have our groundwater plume underneath a industrial building. So they had used chlorinated solvents. So examples of that would be tetrachloroethene, which is PCE, or trichloroethene, which is TCE. And they use that as a degreaser or like a cleaning solvent in industrial and commercial practices. Also dry cleaning is a big source of that as well. So a lot, back in the day, they just had these dry wells where they would just put the wastewater down and we'd get into the ground, and it's in your groundwater. So we had a groundwater extraction system on site where we did do pump and treat, so we're extracting that groundwater to the surface, treating it through some carbon to strip out the contaminants. And I'm not quite sure what we were doing with the clean water afterwards. I would guess that we would probably have to either get it disposed of off-site. If you do want to inject it back on site or put it down the sanitary sewers, you have to get a permit. A lot of the time you have to meet water quality criteria beyond your contaminants because you're reintroducing it back into the system. So that's a whole another layer of things to think about. But we got to a point where we're saying, okay, we're doing this pump and treat system, we're using a lot of energy, and a lot of time pump and treat systems get to a point where the residual mass decreases that it's not really cost effective to continue to operate these systems. So let's transition to bioremediation, but how can we communicate the sustainable attributes of doing this optimization process? So what we did here is a very simple carbon footprint of the amount of energy that we were using and the different type of materials that we would have to use, like the carbon amendments for the P&T and like granulated activated carbon, and then transitioning that to bioremediation. So if you see here, if we continue the pump and treat system in orange, the environmental footprint pretty much stays the same, right? We're not really being sustainable at all. But if we phase out the pump and treat and integrate in bioremediation, you see the blue decreases significantly because we're phasing out that pump and treat. And then the yellow, the bioremediation does have a footprint associated with it because you need to do the footprint of the amendments that you're putting in the ground, the drill rig being on site and so forth. But it's minimal and actually, significantly decreases over time as compared to a pump and treat system. So this was a really good selling point. Again, I'm a big social cost person, so I brought in the social cost metrics. And here in this red is showing if you maintain the pump and treat system, and going into the blue if you continue the pump and treat. But if you phase it out with bio, okay, so the red is showing pump and treat phasing out with bio, that you significantly decrease your total social costs over time. Which was a really cool selling point here too, is right here. So the social cost of carbon is about like $110 per ton. If you look at greenhouse gas trading, like cap and trade, the price per ton is like $25. So think about that difference. There's like a $75 difference if you take in consideration the financial implications of putting greenhouse gas emissions into the atmosphere, right? So we're going to have to spend money dealing with the climate change impacts. When it comes to NOx and SOx, money that humans are going to have to pay because of the smog and other health implications. So there's stark differences between cap and trade pricing and social costs of these metrics. So we looked at, what if we just did the market price of carbon, like a cap and trade price for maintaining the pump and treat system in green? Well, we showed that if we phased out bio, the social cost of that technology actually went under the cap and trade price for maintaining the system. So that was a really great finding and a good way to communicate, why we wanted to move into this direction. Okay. All right, so my last 5-10 minutes, I'm just going to talk about what I perceive are the advances in sustainable remediation and how this field is moving forward. So conventionally, when we think about sustainability, particularly in remediation, we're always thinking about comparing adverse impacts compared to beneficial impacts, right? So it's like, what is the environmental footprint of a remedy? What are the community benefits of a remedy? What's the cost of the remedy? And what are the pros and cons of each of those things? And then you end up weighing those pros and cons to try to determine what's the best outcome. And a lot of the time, you end up doing trade-offs. Maybe one technology has a lower footprint, but doesn't benefit the community. Or maybe one technology really benefits the community, but has a really high environmental footprint. And you get stuck in these situations where you're like, which one do I pick? So it's very focused on minimizing impacts, and you're comparing impacts, you don't really have a good baseline to look at. Now, the field for remediation is moving towards this more integrated assessment approach where we're not developing the technology first and then looking at the sustainable impacts of that technology. We're taking a step back and saying, what are our sustainability objectives for the site? What are the stakeholder needs for a particular site? What does the community want to see for a particular site? Does the agency or the responsible party want to focus on carbon reductions, energy reductions? You know, what are the stakeholder sustainability objectives? And then have those define what your sustainability metrics are, what type of tools you're going to use, and then choosing the remedy that best meets those metrics. So it's taking a little bit more of an integrated assessment approach. And if you're interested in this, Jennifer Pope, excellent paper, it really influenced my PhD and talks about different ways to go about doing the sustainability assessments and how moving towards this more objectives-led approach enables you to capture that triple bottom line in a more integrated manner as opposed to looking at these things in silos. So I recommend that paper. You know, if we don't consider sustainability up front, a lot of the time we just keep implementing remediation attempts. Like you keep running that pump and treat system, which is really costly and resource intensive, or sometimes they just walk away from the site and it becomes no man's land, right? Doesn't return to a valuable asset to society. So having that lack of sustainability considerations early in the project life cycle sometimes ends up in these end uses that are just not uses, pretty much. This is a paper that I was recently involved with where we looked at what type of site characteristics, particularly physical characteristics of the site, as well as the type of stakeholder needs that may be there, and how to better define what type of sustainability performance metrics you want in a manner that is maintaining risk management, that we're ensuring that we're being protective of the environment and human health, but at the same time we're integrating sustainability. So if you're interested in that, we came up with a framework to help you kind of go through that process, and there's a whole list of drivers and barriers and so forth there. And what I find is this helps me go through that integrated assessment process and defining those sustainability objectives up front with stakeholders before getting to that stage where we're doing a sustainability assessment on the remediation technology. So it's kind of like a thought process to go through with the different stakeholders. Reuse of treated groundwater is a really big concept, especially on the West Coast where we have drought-stricken areas. Cert wrote a groundwater conservation and reuse guidance. If you're interested, it's available. It goes over liability issues, emerging contaminants, the yuck factor. Even though you cleaned it up, the public normally is like, ugh, this one's contaminated, I don't want to drink it. So how can you address that? Other type of water quality impacts, water balance and reliability, right? You don't want to extract so much water out of the system and not putting it back into the system that you're depleting the water itself that's within that aquifer, and also economic aspects as well. There's a lot of sites in Western United States where they're reusing remediated groundwater on Superfund sites for drinking water. It's happening. Surveys, they're flexible, inexpensive methods to help engage the public, identify what their social impact indicators are. What are they perceiving as their local economic and quality of life benefits and costs from the different risk management strategies that you're proposing to them? You can look at risk perception factors if you're interested in risk communication and understanding more of the psyche of the community and why they are either accepting of the remediation that you're proposing or maybe not accepting of it. How can you better understand the factors that are influencing their decision-making process? Risk perception also plays in when you want the community to be involved with the cleanup itself. So say there's in Jersey City where you have homes that are impacted by lead-based paint, and those residents are responsible for maintaining their risk management strategy, and they're not partaking in that, you can better understand why. Transparent communication tools, and they can fully participate in the results. I know I've got to wrap up. So multi-criteria decision analysis, if you're interested in how you can engage stakeholders and help them prioritize different sustainability objectives or resiliency objectives. This doesn't have to be focused on remediation, but you want to give everyone a voice. You could come into a room and someone might not feel comfortable speaking. There might be the loudest person being heard. This is a really great way to give everybody a chance to help bring their input and help you come up with the best decision possible. Bring in more social cost metrics like the value of water quality, ecosystem services like carbon sequestration, T&E habitats, wetland making, property value, and aesthetic value. And then very lastly, EPA recently in August 2017 developed ecosystem services at contaminated site cleanups. They issued that paper, which is focused on how can you evaluate how you're restoring the ecosystem service at your contaminated site based on your cleanup, and this can be involved like you're developing a wetland. What is the value of that wetland? What is the ecosystem service behind that wetland, and capturing that as part of your sustainability assessment. So EPA put out a guidance for that. Okay, so I know that was a lot of information. I just want to thank you for your time, and my contributing authors, the Department of the Navy helped with the sediment site. My colleagues at CDM Smith and Insight is another consulting company that we work closely with. And here's my contact information if you would like to reach out to me. So, thank you.